scenario. So you'll want to take a look at these materials I've got here for you. I also included a look at some of the probabilities around the resurrection of Jesus. And then I've got some more information here on Bayesian inference, Bayesian theorem, and then I have a very practical resource here that tells you about the real impact of spam. What does it cost us to have to put up with it and deal with it? And so that's one of the things that a company like MailChimp tries to do for provide a service, is to cut down on that type of issues. So you should you'll find the Mandrill file. It's going to be over there in the it's going to be over in the Foreman files. So you'll want to go over there and take a look at them. Okay. And so I'm going to go down to the desktop, and I think I have the Mandrill file open already. And and I think I've got the, I'll look at this for just a second here. And I'll move that over. Yeah, here are the case files for all my cases. So let me see if I've got Mandrill. And we'll find it there. I think I do. Maybe I don't. I may have to go back in there and grab it out of those files. Now, and that's from the Foreman text. So let me go back in here, and I'll get the Foreman files, and we'll take a look at them. And I think it's going to be over in chapter 3 or it's chapter 2 if I'm not mistaken. Nope, that's the other. So it's going to be chapter 4. Oh, wait a minute. Here I am. My apologies. Let me copy this, and I'll throw it on the desktop, and we'll start to take a look at it. Now, again, what we're doing here, and I'll open that up, is what we call an ex post facto analysis. And what that means is we take some data that have been generated from an event that we know occurred, and we know what happened. Say an analogy would be in medicine when they do when they perform a post-mortem and say the patient died from cancer, some type of cancer, and so they'll go back and look at the medical history and all the things that were done, the treatments, as a way to try to understand how they might prevent it or treat it, and the signs that it was there. So when we use the word, that phrase ex post facto, what we're talking about is after the fact. And those are very valuable studies. And so in this case, we're using two techniques. One is Bayesian analysis, and that is naive Bayes, where we assume that the probabilities of things are 50-50. And then we're also using ex post facto analysis. And we use a lot of he uses a lot of Excel functions. So he treats Excel to a certain extent, like he treats it to a certain extent, like it is like it's a database. And we did this first step, and I'm not going to belabor this, but here's the first tweet, okay? And then we turn it all into lower case letters. Then we begin the process of using substitutes. So we're starting to clean the data up. Now, these tweets are what we would call a type of big data or unstructured data. And so one of the biggest challenge usually with unstructured data is cleaning it up so that we can use it and work with it. And we can try to determine the amount of signal that those data provide us versus noise. And again, signal being a true value, a true picture, versus noise, which is random variation. And the best example I can tell you is if you turn on a radio and go, if you have an AM radio at all anywhere, or even maybe an FM, if you turn a radio, you'll hear the interference. And then you'll find a channel and it comes in just clear. And that's really, that's noise. Same thing if you have your cell phone and there's some problems around the cell phone tower, that type of thing. So we're in the process, and we're looking at, we have these set of tweets that we know are about Mandrill, and there are 150 of those, if I'm not mistaken. Okay. And we're cleaning them up so we can analyze them. I'm right, there's 150. Now, we use the substitute function. One of the nice things about Excel is if I want to really know about a particular function, I just click on the function symbol there, and it will give me the dialog box or the function arguments. Okay, and so you can see we're starting to clean this up till we get it down to what we call a token, and that is something that I can count that's representative. A dollar bill is a token. A quarter is a token. A flag of a country is a token. So we're going to try and clean this up. Now, we got over to this point, and then we ended up, okay, with our substitute, and then we end up with our tweet, okay? And the tweet starts at column I, excuse me. Now, we did the same thing about the others. These are tweets that we know are not about Mandrill, okay? And we begin to clean them up. Then we have our app tokens, okay? And so we've got the tweets, and we know these are tweets, okay, that are about the product, okay? And then we begin a process of examining their length. All right, and we've got the space position, and we're going to start at 0, then move on over 1, 2, 3, and count the length of each of these tweets. Now, we've got 150, so we're going to be doing a little bit of work as we go through these and see their length. And so we've got this first token, and that's blog. And I provide you some resources that explain to you the if-error function and what we get, okay? And we're going to use also, we've also embedded the mid, okay, function, and we're going to test that condition. And if we get an error, that's what we provide. We provide the value of a dot with a set of parentheses, okay, around it. Not parentheses, excuse me, double quotes. And then we get the length. And notice what I'm going to do. I'm going to take the length of C2, and there's C2. And if you look at the characters in C2, you're going to see, and that's blog. It's the word blog inside of brackets. And I'm going to count. Bracket 1, the bracket is 1, the B is 2, the L is 3, the O is 4, the G is 5, and the last bracket is 6. So we know that the length is 6, okay? And we're going to go through and evaluate each of these, okay? And notice we're always starting from a space position of 0, and then we begin to build down here, okay, as we work our way through. And then we start, and we come to the first, and here's the space position of using, all right? And if you come over on row 152 and you look, you're going to see USING. We start at space position 7, okay, because we've worked our way up to that point. And then we get the length is 5. All right. Now we've gotten all of those lengths, and these are the app tokens. These are tweets that we know are about the product. And again, I've provided you ample resources, and the text also walks you through that process. Okay, so before I go any further, I want to do this. I want to go back over here, and I want to open up Vital Source, all right, and we'll go into Data Smart, okay, and we're pretty much back where we started here. Here's the prepped tweet data as he talks about it. And the nice thing about this textbook is he's going to walk you through step by step by step. Now, I'm not going to belabor this a great deal except to say 2 things. One, we've used Excel and used its functions to clean up what we call some unstructured data. Then we're going to use it to test the probability of whether or not a tweet is about the product or not. Now, we already know, but if we find something that's an error, we're going to be able to act. And you remember we talked about that. I showed you the truth table, or the type 1 versus type 2 error. And so the people at MailChimp are trying to work off of that model. Remember, in management science, we always use a model, okay? And typically, the most powerful model is an algorithm or some kind of mathematical model. And in this case, what we're saying is we're trying to balance between two opposing things. One, that our measurement is too stringent and it gives us a false positive. Okay, it says this is not about the app when it is, or a false negative when spam comes to our email. Okay, and we say, well, wait a minute, and we don't consider it spam, but it's actually spam, and it gets through our system. So it's a matter of balancing the two of those off. And I wanted you to see this case so you could understand that issue, and a very extremely valid technique for looking at these types of unstructured data. Remember, now we did the cluster analysis, okay, when we tried to identify market segments. And this time we're trying to differentiate between tweets that are about our product versus tweets that are not about our product. This is not too much different than what governments do when they're surveilling emails, when they're surveilling phone calls, and all this stuff about metadata, okay, that you heard a couple of years ago. The metadata give us some overall type. That it might be an area code, it could be a country code, it could be from one city to another. It really depends. And so the people who got all upset and whacked out about metadata, this is just my opinion, we're probably not thinking very clearly. You know, if someone is calling a certain country all the time, and the people in that other at the receiving number are calling them all the time, and the person who has that phone number that's making the phone calls just happens to go over to the internet and download the directions on how to make a bomb, I think something's going on. And and that's the type of thing that they do as they monitor these. But in this case, we're just trying to find out, is the tweet about our product or not? And he walks us through on this issue of splitting spaces, okay, and walks you through the exact detail. That's how you get those. And he says we're going to stop at 30 tokens, okay, but we've got 150 tweets, so we'll end up with 4,500 rows for each of these. And there's the initial token, and of course he walks you through the whole thing. All right. I don't expect that any of you would be able to build this type of model, nor would I expect you to have to. When you go to work, you will probably have, you may be asked to work with some unstructured data, and this would be a valuable resource for you to have to come back and say, but it's going to depend upon the type of data you have. And as I've mentioned before, out there in the real world, people who work in the hard sciences particularly use R programming, because R programming has the ability to take data and literally melt. They have a melt function, and what it will do is it will just take the data, and you can say, okay, these are the columns that I have. So everywhere I find this word, it's a column, it's a dimension, and then I just start to put stuff in rows. And it can handle large data sets. But the only problem in my mind with R is that it's open source, so you have all these different functions. I've taken a couple of courses on it, and you can use it, but I frankly found it, I said to myself, I don't know if as a business person I'd ever have these type of data, number one. And number two, if I have a data set that large, I'm going to probably use another application. So he walks us on over here on the every token, and then we start to do the counting the probabilities. Now, I want you to notice he goes in here and he uses a pivot table. So I'm going to diminish this down for just a second, and let's go back up to the table, and we're going to look at the app tokens probability. Now we've got, and we add 1 to every item, and that way we normalize the data, and then here's the probability. All right. And we've got C5 over C828, and A28, okay, is the total number of tokens. Now, again, he decides, and wisely so, to go ahead and use the LN, the natural logarithm. You say, why do you do that? Well, it's the same reason that you use ratios when you work with financial data. They wash the data clean. They get out the distortions of the size and effect. And so he's using the natural logarithm here, okay? And he's standardized these data by everything gets a 1 added to it. So it's not so minuscule in terms of probability. And then he applies the natural logarithm function. And so now we have something we can compare. We can compare things because they're all in that state. They're in a natural log state, and that's, again, like I said, that's no different than what we do when we use a square. We get something and we use the square root of it, or we use ratios. We're always trying to take out the distortions so we can get to the signal. And just a very simple example would be, if I own, okay, let's say I'm Apple and I made $1 billion last year. If I'm going to make if I'm going to have a 10% increase in profit, I'm talking about $100 million to get to 10%. If I have a $100 million company, I'm talking about increasing sales by 10 million. Okay, which is a whole lot different than 100 million. So the scale, the distortions that get involved with scale get washed out. Okay, and we're always looking for that. We're always trying to find a way to wash out the noise and get to the signal. So he's got the natural logarithm here, okay, for each of these. And we're going to come down, and he's over in row E. Column E, pardon me. And we've got these probabilities. All right. And we get the log number. And again, we've got all of these different tokens, okay, and their total. And we've added 1. So we know the probability of each of these being about the application mandrel. And then he just repeats the process over here on the other tokens probability. And again, in the text there, he walks you through that process step by step by step, okay? And if you want to take the time to try and duplicate it by following these directions, please feel free to do so. But the main thing I want you to understand is that we do have ways to deal with unstructured data. Particularly, there's a lot of stuff in business that is written data. A lot of things that we can easily overlook. And for example, I think it would be interesting if you really, and for some of you, you're going to head to graduate school. There may be one of you, 2 of you who someday go on and go into college teaching and become a prof, and you'll be asked to do some research. And there's we have literally trillions of bits of data out there, of documents that companies produce, or the minutes of board meetings, or all kinds of things that are there for us to cull through and discover a lot of insights about business that we couldn't do otherwise. So we've got the other tokens probability, then we do the test tweets. Okay, now here's the tweet, and then here's where we've done all the cleaning out. We go through and we go through that process of cleaning up the tweet. And over here in column B, we make a determine, is it an app or not? Now here's column 1, okay? And we have 10 of these that we know are apps. Then we put in the others, all right? And we've got 10 that we know are others. So these are our test tweets. So we know these 10, they're about the app. These, then 11 through 20, those are not about the app. And we have the data and we begin to clean it up and all that. Now we do the test and we do a prediction, okay? Now, this is pretty simple. We have the tweet number, okay? We have 20 tweets, 10 of them ostensibly about the app, 10 of them ostensibly about the other. This is where we see how we're using naive Bayes. We're just coming from the idea that it's either about the application or it's not. There's no weighted probability. This would be no different than if I said, okay, I'm going to give you $1 million, okay, and you're going to build a portfolio, and your portfolio is going to have, let's see, you're going to have a tech stock, okay, you're going to have something like in the commodities, you'll have some government issued securities, and let's just stop at those 3. That'll make it easy. Now, if you have a weighted portfolio, you're going to have some assumptions. One of those is obviously going to be the rate of return, the expected rate of return. The second is going to be the probability to which you believe that the expected rate of return will indeed be met, or maybe even exceeded. And those, in that case, with 3 of them, it would be 33.33%. And if we do 4, then it's easy. It'll be 25% in terms of of just a raw portfolio. Now, if I say, well, I think I have a better chance with the bonds to reach that particular return, then you're going to weight those, and they'll be different, but they'll all add up to 1. That's all that's going on here, except with naive Bayes, I say, okay, I just assume it either is or it isn't. That's why they call it naive, okay? Now, let's roll over here, and we'll see over here to the class, and then we've got the prediction. And let's roll down here and see this first one. Now, this uses a conditional statement, and again, I provided you've got the textbook, and if you're really interested and it's something that you really want to be diligent about, if management science in some way just kind of appeals to you, then you've got the resources there, the book plus all of my notes to see this and get it. And I can tell you that this is one of the best, simplest ways I could possibly show you in terms of how we can use management science. Even in this stuff called unstructured data, we use a key principle, and that's called, or a technique, and that's called ex post facto, after the fact. We collect data after something's happened in order to learn about what we can expect to have happen, okay? And here in this function argument, it's simple, it's if, and we have a logical test. And if that's true, then the value, if true, is app. If not, we give it other. And that's all we've got going. And then we just drag and drop the thing down. Okay? Here's another. Now, as we come down here, we're going to notice that we're flowing along really wonderfully until something happens. Now, 1 through 10, we know are apps. And so far, our predictive model is working. And we're comparing C34 versus C57. Now, C57 is a probability, okay? And this probability versus C34. So C34 is larger than that. C57, it's an app. Otherwise, it's an other. And so we have this prediction, and we're rolling along. And then here at number 19, we get this. Okay. So we have this app that's incorrectly, it's incorrectly identified because it should be other, but it shows up as an app. All right. And we'll go back up here. And so our predictive power on this is pretty good. We're talking 20 trials. And out of 20 trials, we had one that went bad. And so we got a 95% success rate. But again, we got to go back to that truth table or type 1 and type 2 error. Okay. And and look at what happened with number 19. Number 19, it's pretty simple. I called it an app when it was not, okay? And so I have a, if I'm looking for the other, I have a false negative because I've called it an app. And by calling it an app, I don't call it another. Think through all that, and you'll go, oh, okay. Again, now I also like to show you this so you can see that Excel will often, I think, be your go-to tool if you've got some heavy-duty number crunching to deal with. Now, many of you are going to be fortunate enough to go out to work and work with SAS Visual Analytics or SAP or some of those other packages are out there. Some of you may not, and I can assure you that this book, and there's some other textbooks out there from folks that work with a lot of these types of data sets that will tell you that Excel can do a lot of the heavy lifting that you need. So, 19 out of 20 times we were correct. That's not too bad. Now, if I say, okay, I can extrapolate that out to if I do 100 of these, then basically I'm going to have what? 5 of them that are incorrect. So I have to be careful because of the law of large numbers. The more of these occurrences or these tokens that I count, even if it stays constant at 5%, when I start talking a million, I'm talking how many tokens? You can do the math. And this becomes extremely problematic if we talk about, this becomes very problematic if we talk about, say, the probability of a terrorist event. I guarantee you that every single time there's any kind of major athletic event that somebody in somebodies in government agencies are watching that carefully and assessing the threat that could occur, because when you get that many people together, you just never know. And to give you a case in point, it's been a few years back, but OU, Oklahoma University football, had a football game with Baylor University. And I remember this was on a Saturday night, and I had just started using this textbook, and we had just talked about this case, and there was a guy who blew himself up in a car, and I guess he miscalculated on how much ordnance he needed or whatever, but he really didn't do much damage. But his intention was to blow up his car and kill a bunch of people. Well, he couldn't get close enough to the stadium, and I can tell you how he should have done it, but I'm not. But the bottom line is that we have to be careful that the law of large numbers can creep in. But this, and let me say this, the book, Data Smart, the guy, he's a young guy, okay, and he's kind of smart aleck, likes to tell his stories and this and that, but he's absolutely off the charts smart. He's so brilliant. And this is just a beautiful thing to behold when you think about it in terms of what it can do for a company. Okay, well, we've talked about that and we've groused over that. So you've got the mandrel. And like I said before, it's up to you to determine if you want to sell. I've seen an example of how we can deal with some of these data and do an ex post facto study and do a predictive study. We've also and we've used that model there, okay, of naive Bayes, and we've also done a cluster analysis, okay, to determine clusters of those who I think acted on a particular offer they had on wines. So this is very useful stuff. Now I'm going to close this off and I'll save it. I'm going to go back up to my page, and of course he's going to walk you through all this business. And again, it's there for you to take a look at. Now I'm going to go back home here for a moment, all right? And I want to go over to our management science textbook because we have another assignment or issue that we want to deal with. And so we're going to look at that, and we're going to talk about single arbitrary, which is going to be due on the 26th. Now, I've got a place here for you to upload it, all right? And let's take a look at it for just a minute. We're going to be looking at the issue of queuing theory. Queuing theory is how things are served in a line or multiple lines with multiple service units. And single arbitrary means this. We serve a single customer or arrivee at each time, and we have an arbitrary amount of time that we spend with them. You say, what's a good example? I'll tell you a good example. When you were a kid, or maybe you still do, you go over to, you go to the fair or somewhere, or you go to Frontier City, and you get in a line, and you put in a token or pay some money. And then what's next? You get on the ride, and the ride lasts 3 or 5 minutes, and it turns you upside down and throws you sideways. It does everything it can to give you the thrill of a lifetime for an 11-year-old, and that's to get nauseated, okay? And if you're a kid like I was, my favorite thing was 2 or 3 hot dogs right before the roller coaster, which was a spoiler alert for my older sister and brother who said, I'm not riding with him when he's had all that. But again, you have a single arrivee, okay, and you have an arbitrary amount of time that you serve the customer. And so it's pretty basic. So that's over in page 525. Now, what I ask you to do is this. I ask you to use the goal seek to obtain the service cost per channel. And then I ask you to make an assumption that the waiting cost per unit is $1.16. And I say, assume you want to obtain a total cost per period of $2.99. Well, I'm going to go over here to, the book, okay, and grab it here for a minute. Make sure I'm still in good stead. I'm recording, okay. And I'm over here in Vital Source. Here we go. Hi there. And I'm in the single server waiting line with Poisson arrivals and arbitrary service times. Now, let me talk about the one thing that I didn't mention as I talked about this model, the Poisson arrivals. You say, that sounds vaguely familiar. Yes, a Poisson distribution is one that's more like a wave or a stair step. Think about it for a moment. If you are in the restaurant business or the fast food business, everybody comes in at 11:30 or 12 or whatever, and they order their food. And then it dies down. And then you have a run for dinner at 5:30, 6 o'clock, all that business. And then the next morning, if you're open and you serve breakfast, you have a run on the breakfast. Now you'll notice that almost all of these fast food people now are open 24 hours a day, 7 days a week. Why would they do that? What they're trying to do, first of all, is to hedge some of the risk that's implied by having stair steps. So they're trying to smooth the arrival patterns. Okay, that's all that's, and the other is they're trying to get more of a continuous production on some of their breakfast items rather than batch. So when somebody says we serve breakfast all day, if you're like my wife, who is a breakfast freak, the idea that at 4 o'clock in the afternoon or 5 or 6, for her, it's 7 o'clock at night. She's having, if she can have an omelet and some biscuits and gravy, she's in heaven. And where she puts it, I don't know. I can look at the stuff and put on 35 pounds. She takes it, eats a big helping, and she's just, so lucky her. So we've got this Poisson arrival and the arbitrary service times, and again, this is covered in 525, right? And we see the characteristics of that model, okay? And they're talking about the M, the G, and the 1, okay? We have minutes, arrivees, okay? And let's look back here for just a moment and see what they mean by that in terms of waiting line models. M is a Poisson distribution. G, you have a D or a G. A D designates that the arrivals are deterministic or constant. You say, what would that be? A deterministic or constant arrivals would be flights of all airlines coming into an airport. Okay, all of the drivers going to the gate there at Tinker, going to the gate at the Turner Turnpike halfway. Okay, and I remember one time someone asked me, why is the Turnpike? Why do they have the gate in the middle? It's very simple. They siphon off demand at those different exits. And the different exits, they tell you, you must have exact change because they don't have people manning those. And so if you're driving along, you get smart and you buy a Pike Pass, and then that's even less stuff. You just drive through and it hits the scans you and you're good to go. They don't even have to worry about you paying somebody. But if you're a traveler, etc., then if you're not siphoned off to one of the towns, say like Chandler, you head in, and that's how they control that constant flow. Okay. Otherwise, if it's a G, we just think it fits some kind of probabilistic model. Okay. And that's all we're talking about. Now, the authors walk us on through this and show us the example, the model, and they give this seafood supply. Okay. And we get the constant service times. Okay, and then they start to talk about a multiplier when we have blockage of customers, etc. But we're going to stop just purely at this one model. Okay, now, as usual, we're going to go into the Anderson file, and I'll go back up here, and that's chapter 5. I think we're in chapter 5. Or no, we're in 11. And I'm going to go to the Anderson. I'm going to open it up. And we should find single arbitrary. Aha! There it is. Now, let's take a look at this jewel. We'll move Mandrill out of the way. There's Cardinal Buddy. He's smiling because he knows spring training is far ahead, but he does not watch the World Series. I'm happy about that. All righty, let's open this jewel up. Okay. Now, let's see what we've got going on. Here are the basic assumptions. We have Poisson arrivals, like stair steps. We have arbitrary service times. Now, this tells us there's a dynamic. The Poisson is not constant. It's sporadic. It's like a batch manufacturer who sits around and waits for people to call with orders to make me 100 of these or make me 500 of these. Now, I realize it's 11:45 and I started a little bit late. So for those of you who get antsy or whatever, you're free to go or stay at 11:50. You're free to go because I'll record it and you can look. So if you think you'll be late for class or something, you won't hurt my feelings if you bug out. Okay. Let's look at this for just a minute. We have these two assumptions, but we have this arbitrary service time. So we're balancing off these two things. And you remember at the start of the course, we talked about the things that are controllable and the things that are not. Okay? And service times, how long it takes us to service something, that's arbitrary. We're in control. But the arrival, that's a different critter. We're not in control. So we've got some data that we start to attach to this skeleton, and we've got the arrival rate. We've got the service rate. So it's, how often do they arrive? How long does it take us to service them once we do? And then we have a standard deviation of service time. Now, if I have a standard deviation of 1.2, okay, and I have a service rate of 0.5, I'm not going to go through the usual thing where I ask someone to tell me what it is and we all have to sit here in silence. I hope at this point that you go, well, dummy, I'm going to put if it's a 0.5, this is my service rate. And if the service rate and if the deviation is 1.2, then this would be 1 sigma above. This would be 2 sigma above, okay? And this would be 1 sigma below, okay? And this would be 2 sigma below. Now, I think if I were to say, which end of this spectrum do you want to be on? You'd say, well, I want to be over here. Because if I'm consistently beating this service time by 2 sigma, okay, I'm in good shape. And it's pretty simple. That's going to be 2.6. That's going to be this is going to be 3.8. And this is going to be 1.7. As they say, time is money. And that would be, pardon me, put the 1.7 here. And now I've got a 2.9. Okay. So I can see, now, if I, here's why I say, if some of you need to go, you do, but if you stay. If you've ever heard me talk about Southwest Airlines, I think I've gone through this before when we talked about, we had that one airline, but here's where real money comes into play. If I can consistently be below this typical service rate, I'm saving money. Pardon me, I'm making money. You say, what do you mean? Let's say that those are minutes, okay? And so, or they're units of 10 minutes. The faster I service a plane, the faster it's in the air, the faster it gets to another destination, and the faster it's ready to be refilled, etc. So if I can save 30 minutes on 150,000 flights a year, I've just saved 5,000 hours of flying time, which means I can put another plane into service and pick up the additional demand, etc. And that's one of the ways that Southwest has revolutionized the air aviation industry, the passenger airline industry, by doing that. Okay, and it's the same with people like FedEx or UPS. When they have when FedEx and UPS get a new vehicle, okay, they have specialized vehicles to carry goods, and if you ever get something delivered to your house or whatever from UPS, don't bug them and stop them, because they'll probably say, "Where are you going to go?" Just if you take a peek, you'll see that those trucks are all different because they carry different types of packaging and different types of loads. Well, we've got some operating characteristics here that are probabilistically based, and you can read these and you can see, okay? And then we do an optional economic analysis, and we can figure out the waiting cost per unit and the service cost per unit, and then the total cost per time period. So I've given you, okay, a little bit of a case to work with, and you'll have to take a look at the operating. You'll have to figure out how to compute the waiting cost per unit and the service cost per channel, and then the total cost per time period. And again, in that assignment, okay, let me get back over here to where we were, okay? You would be smart to copy the verbiage, because that's the assignment, insert the text box into your copy of a single arbitrary, figure out how to get those totals and do those numbers and run them. Just take a shot at it, try it. And when you say I'm using goal seek, well, it's pretty simple. You're going to use the goal seek, and you're just going to put in, a certain figure that's your goal, and the figure that's got to be changed for you to reach the goal. So it'll be a little bit of work. And then on Monday, we'll take a look at it and we'll go over it. This is our first little dip of the toes into the world of arrival and networking and arrival times, generally called queuing theory. And it's important. And as you'll see, what I hope, I hope that beyond just, okay, well, this would be a way I'd figure out, service times. What I hope is that you'll also look around the world at things like the lights in your town, airline traffic. All of these things are dependent on these models. So this is one of those important courses you have, because it shows us we have so many ways we prove that these techniques and these models work. And they can provide us some tremendous, tremendous tools to use when we try to deal with the world. If I'm wanting to, and let me give you one good example of this. Back at the end of the Second World War, the Soviet Union and the United States were the two great superpowers. They were left. The city of Berlin in Germany had been the heart of the Nazi regime. And so the Allies, to them, Berlin was a prize. They split it up. And the Russians people are very paranoid about Germany, and rightfully so. Germany's invaded them twice within the past 100 years. So it would tend to make you a little paranoid. So they wanted a buffer, and eventually they built a wall. Now, the city of Berlin was in the middle of what was called the Soviet sector, which was that sector part of Germany. This is all foreign to you, because all you know is Germany as a country. Well, to make a long story short, when the Soviets decided to cut off Berlin and put pressure on the Allies. The Allies, Harry Truman was the president, had a choice. Do we go to war, or how do we figure this out? And what they did was they did an airlift. And go out and Google it and read about it. It's one of the most incredible things how the Allied, particularly the United States Air Force and what was in the Army Air Force, supplied practically an entire city of people with food, clothing, medicine. I think the airlift lasted maybe 6 months, maybe a year. It's unbelievable. And so that's the kind of good that you can do, because if we had not had that tool, we hadn't had that alternative, our next step was we go to war. And we'd have World War III. And it would not have been a good experience, because at that point, everybody had an atomic bomb. Well, folks, I'm going to leave you with that. A little bit of work to do on single arbitrary. And anybody have a question before I wrap us up? Where's ad break? I know, ad drop, etc. Anybody? Okay, if you don't feel comfortable asking a question here today, obviously you can send me an email, but this single arbitrary is due on the 26th. Thank you so much, and pardon me, and have a good weekend. Stay safe, and I'll see you Monday.